can even sit in first row. You know, I specifically for you had a shower this morning. Okay, so welcome everyone to the last round of sessions for the ICIST Conference. It's my pleasure to be your session chair today, and we will have a session on information technology applications as a special session for Internet of Things in mobility applications. I hope you all enjoy the talks. We have 5 talks, so that means we don't run into danger of running out of time at the end. So we have time for a few questions after each talk. And I would like the first speaker. So the first talk would be by Mr. Kabashkin, and he is using embedded cloud technology to analyze video communication channels, but I think he will have a lot more details about this topic for us.
Yes.
Now, so welcome.
Thank you. Thank you. It's a very pleasure for me to open our last session. I think that title of my presentation, Analyze Voice Communication Channels for Ground Segment of Air Traffic Management System, is quite specific. So I would like to give some introduction to the thematic of this area. Of course, today aviation is one of the most important mode of transport, and you can see the traditional classical roads of aviation roads, how it increased from year per year, yes, in Europe. And today, practically in the world, it is quite a hard picture, and I would like give you introduction and show one of the model that we prepare for air control. You can see one day of aviation traffic in Europe. You can see how much aircraft in the environment and the time, current time. So you can see how hard traffic today in Europe. Soon will be the most interesting picture in another dimension. You can see the main gates, London, Paris, Germany, airports. Who will come back by aircraft tomorrow? Evening, traffic is not so hot, practically no flight via Atlantics. Okay, now it's time to sleep. Yes. Practically today, at each time, each aircraft has monitoring and control by controller of aircraft system, and all environment divided by altitude and by road under different types of controller. You can see that practically one types of controller monitor aircrafts at the aerodrome zone, another during departure, then during flight, then aerial, and else one in aerodrome control. Practically all environment have different types of so-called air corridors, and each part of these corridors monitoring by air traffic controllers, independent traffic controllers, and each part of these corridors have independent communication and different frequencies. It is direct communication between pilot and between air traffic controllers. There are a lot of air traffic zones, so practically only at the airport the controllers sit down in the special towers. There are some controllers here, but during roads, monitoring of the aircrafts carried out by special controllers that sit down in special centers. There are a lot of such kind of centers, and it's multi-channel systems. So it's quite large and quite difficult system. But today, practically, we have only one means for communicate between pilot and air controllers. It is redundant communication network for air traffic management systems. If we have channels of communication at the air traffic management control center, each air traffic controller have two radio stations, main radio stations and redundant radio stations. Each of them has different independent frequency for direct communication with aircraft. So we have failure main radio station, controller switches to the redundant radio station. So it's quite simple and quite reliable system. But of course, today we say about new generation of ATC communication on the base of IP voice communication systems, and for new generation systems we have cloud-based communications. We have mobile nodes at the aircraft because there are a lot of different navigation, communication, radar system on the board. And in each airport we have home ground embedded cloud for different types of communication, and remote ground embedded clouds, which directly involved in one common environment of Internet of Things practically today. So in this case, there are, and we need have a balance between flexibility of services of such kind of systems. We know this flexibility of new information technology, but we must keep the reliability and the resilience of such kind of systems because it's very important from security point of view. In our work we analyze reliability of these new systems, which has one common cloud of voice communication systems with different human-machine interface of air traffic controllers, main and redundant systems, and health and usage monitoring systems. Practically, in this case, we switch from traditional model where each channel have two radio stations to more flexible systems with some common set of redundant radio stations. So for such kind of model, we built Markov chain state transition diagram for different types of number of repair bodies, less than number of redundant systems, and less than total number of systems in voice communication system. And we analyze the redundancy, the reliability of these common systems with two modes, failure modes of automatics of embedded cloud, with one type flash switching and no switching, which is quite important for automatic of such kind of systems. Practically, we have a lot of different expressions for channel availability, I don't show all of them. You can, if you interesting, will be interesting for you in our papers. But interesting that then we analyze reliability of these two types of voice communication systems. We would like to analyze availability of one channel in communication channel in traditional systems and in new one. And of course, it's the new systems will be better if availability of this system will be better than availability of previous one. So we analyze and have some numerical example, because unfortunately today we practically has only one types of hardware for these new systems, and this hardware is produced by RATNYČŽ company. We use and analyze all equipment for home ground embedded clothes of these systems, and have modeling of this reliability. And at this picture you can see the reliability degradation factor shown as function of number of communication channels with different number of n standby radio station. And in this case we can see that practically the new generation of communication system have practically the same availability as equal 1. It's the same availability for H channels only for 2 redundancy systems, not for H as in previous systems. And for number channels less than 24, we need only 3 redundant systems, but not 24 as in previously one. So of course it is quite efficient from hard point of view systems, but we have additionally a lot of flexible services for such kind of systems in according of cloud technology and IP voice communication systems. And for these results we can obtain a requirement for availability for different modes of transport, for flash and node switching. For example, if we say about 20 channel systems, we know that we need only 3 radio stations, redundant radio stations, and we can obtain different types of requirement for such kind of equipment. If we need these parameters, it's okay. If no, then we can increase this reliability. So practically for this type of systems, in today's communication channels we have 40 radio stations, but in alternative systems with cloud technology we need only 33 one. So it's quite interesting result, but in the same time we have reliability more high than in previous systems. So it's small results of our work, of our models, and we have in conclusions the same words as I already told in my small presentation. Yes, thank you for your attention.
So thank you very much for the presentation. I was happy you didn't go into all the formulas in the detail. It would have probably taken us the remaining of the day to check all the details. I might have seen a small mistake at some point.
Yeah.
No, not really. So, does any one of you have a question?
Maybe I would have one question. It's not related directly to your paper, unfortunately, but I was always interested why, when we have some accident, plane accident, why, for example, the planes currently don't have any like sensor or position sensor that would direct us to the place of the accident directly, because they are always saying, yeah, the accident took place around roughly 100, 200 kilometers per meter?
It's not correctly, because the airplanes have such kind of sensors, and as we know, the security of airplanes is the most high between among all other modes of transport. Yes, and now in Europe we will discuss the new concept of free sky. Then airplane can fly in the sky the same as practically the same as we walking at the land. Yes, why? Because we have quite good, quite reliable sensors, different sensors, and special devices, radar, navigation systems, and others. Then have very precision data about location of airplane, not only one airplane but all airplane in the sky. So practically each aircraft, large aircraft, have such kind of systems. The problem another, in the low altitude there are a lot of small aircrafts which not unfortunately have such kind of systems. And another new problems is a lot of drones in different applications, which can give additional problem for large aircraft. So if we say about large altitude, there are no problem, but altitude about 400 meters, there is a problem. So if you can see the different types of controls, but it's the most difficult part, this one, because unfortunately there are not only large aircraft but different types of aircraft. At the stationary position there are no problem, and for large aircraft there are no problem. Maybe you listen that the main problems are then departure and then arrivals aircraft. So that is the problem in main.
Okay, thank you.
And it might be perhaps that if we have an accident, which is not often with planes, well, it's more than a car accident. You know, when you just bump into, I don't know, some trash bin. Usually, when a plane falls from the sky,
of course, one of the main reasons for any accidents is human factor. Because sometimes a pilot not switch on some systems. It's a problem.
Okay, thank you very much for your presentation. So we have then the certificate for your participation.
Thank you.
Thank you. And now we come to our second talk, which is by Mirko Lammert. So we have today a somewhat Germish session with few people from Germany and two people who are not from Dortmund, which is nice. So it's not a Dortmund only session. So well, from my home university, I welcome Mirko Lammert, and he's talking about model-based architecture for road traffic management system. So now we are not flying, we are back to the ground with different problems. The floor is yours.
Thank you. Yes, I'm Mirko Lammert from the University of Applied Science and Arts in Dortmund, and want to present our paper towards a model-based architecture for road traffic management system. First, I want to show the structure of my presentation, where I will start with the introduction to give you a short overview what we have done, and then the architecture of our road traffic management system. Then we identified some system component meta models and want to make them reusable. Then I want to to talk about the conclusion and the future work. So, yeah, the intelligent transport system domain yeah, benefits from the IoT paradigm. So it's a bit that we have embedded systems, software, and so it constitutes to the cyber physical systems, which interacts with software and physical systems. So the RTMS is for collecting and providing traffic data, and we solve the CPS design challenge for modifiability. So we want to change our detection algorithm for the vehicle count and detection of speed and length, the heterogeneity of the detection hardware, which is a roadside sensor, the flexibility, so we can use and propagate our collected information over several protocols to other devices or platforms. So we investigate of the MDE capabilities to cope with the cyber physical system challenges in our system. So we benefit the MDE. So we generate our documentation. We made a modeling language, possible model. We define a meta model per component of our system, and the composition of the meta models we want to reference and reuse modeled artifacts, the RTMS. The meta models abstract syntax by these this means to model artifacts. So now I want to talk over the architecture of the system. This is a picture of our a road-based system, which the project partner installed and is working on. We have 6 delineators, 3 on each side of the road, with 7 radio connections. And if a car or a truck or any other vehicle drive through the system, they measure the RSSI value to get to calculate the length of all 7 values and the speed, and to say it's a car or a truck or a human was pathing the system. And out of this, we made our architecture of our system. We have here the 6 delineators. One is a master delineator, which communicates with the platform over GSM. We have 2 endpoints with one is a high priority endpoint for wrong way detection, that we can act immediately and inform other people over a smartphone, and then we have the normal priority endpoint for right-way drivers to get the speed or length information and so on. On the other side, we have our server on we were executing a Wildfly application server, which uses a MySQL database, and we deploy our platform with the identified components, which are on the next slide, and have some interfaces for REST to get information on the smartphone, DATIC2 for a marketplace information, so you can change information on it, and the RDS TMC for in-vehicle information on the navigation system or radio, if it can this technology. So here are our components of the software platform. We have the database access, which is the object-oriented view of the low-level database. For this component, we have already a DSL written. Then we have the raw data receiver, which get the connection, the information from the delineator masters with the two endpoints, the high priority and the normal priority endpoint. So, and it's required the database access to persist the incoming data. Then we have a calculation component to calculate more information from the raw data, and because we get only the RSSI values, and then we calculate the speed and length and deduce information out of the raw data, and it requires the other components, so it can handle the wrong rate drivers with the high priority endpoint, and then persist it on the database and so on. Then we have the data provider, which is the interfaces for REST, DATIC2, and the others to inform or as a smartphone app or get it to the marketplace, and the user interface with user management and the dashboard for all the information, and to add a new system to our platform. The next I want to talk about three components: the database access, the calculation, and the data provider, for which we have meta models, because the raw data receiver is much simple and easy, and for the user interface we see not the necessary to build a meta model. So the database access, we have the main element is a database entity, which represents the object-oriented view of our database tables that can hold columns with unique values and have association between other database entities. And the database access is already as DSL already. And then the calculation component, we're still working on it. We have we want to build an algorithm to calculate the speed and length out of the raw data, and have here the algorithm. It's like a normal function in Java or C or whatever, and we have some input variables and at maximum one output variable, which we can have statements like a loop or condition and so on. So typical constructs of program languages, and the data selection, which is a connection to the data access model we want to use. And the data provider is for the interfaces. It uses the service concept, and the service is viewed as a black box which can receive a request or produce some response. and so we want to propagate the calculation values over these interfaces, and so we can view each component as for the data provider. Also, DSL is written and ready at the so we can view each component as a self-contained language component. So we can expose the metamodel element instances to be referenced in other component metamodel instances, and each language component defines interfaces for mutual instance references. So what I talked about the data selection in the calculation to get the reference on the other DSL, and instance of metamodel elements defined in one component might be referenced in other components for reuse. So we expressed this in via UML and have some visibilities and relationships added to the normal UML. So we have a visibility attribute for components. It's design time only, so we can change the metamodel only at design time for the database access. And we have exported, so that is the signal that we can use this element of the metamodel in other components and metamodels. And we have the visibility of hybrid to so we can change this on design time and runtime. So we can change the calculation algorithm on runtime or at design time. So, and then we have the association stereotypes for relationships. So here the data selection from the calculation component imports the database entity from the database access as a hybrid. So the calculation can change, and the database access is also given to our raw data, and we not need the type of the entities, so we hide it here, and the same is from the data provider to the calculation. So we import the algorithms and provide it over the interfaces. I have an example for it. We have here the database access model instance, and have two entities, the parking log and the parking space, with some columns and a link between the parking space to the parking log to get to save the information and then get it out. In the calculation, we have an algorithm that calculates the average truck space on a parking area, and we have the link between the parking space entity here and use SQL state or SQL-like statements to select the parking space where the name is the given name from the function. And then we want to get the log from the space in a time interval and then iterate over it to count the trucks that are standing on the parking space and give the average back. So here we have some well-defined interfaces for the DSLs and metamodels to get this connection done. And for the data provider, we invokes here our algorithm and receives the name and the dates of the data we want to calculate with, and then propagate this over a REST interface with as a JSON. So the conclusion is we use the NDE techniques for our road traffic management system, and we identified the components of the RTMS, creation of the component specified meta models, and you make the composition of meta models via UML attributes, stereotypes, and dependencies for instance reuse. So we're still working on it. So we are developing the calculation DSL, and the database and data provider DSLs are already done and developed. So in the future we want to extend the platform architecture to use the proposed modeling means for meta model instance, referencing and sharing these meta models, the extension of the database access. We want to extend to support non-relational databases for the expected large amount of data, and we want to create a UML profile for modeling compositional relationships between language meta models. So that's it.
Okay, thank you very much. Okay, that was the shift from mathematics to software engineering and modeling at its finest. Any questions here?
7 slides, please. Yes. What means these sensors or some scales? S, M, G, and so on.
Yes, this is the name. The partner gives the name for these sensors and the receivers, and these are the gateways to get the information from these delineator to the master and send it over GSM to the platform.
Do you use only one type of sensors?
At the moment we have 2 revisions of the hardware, and on each system has the one type of sensors at the moment.
Okay, and what functions has the road traffic management systems on the base of collected data?
At the moment we are counting parking spaces on the highways to for truck information systems to tell the truckers the parking space is full, go to the next, and then in the future we can count cars on the highway and can detect Stau.
Traffic jam.
Traffic jams. Okay.
But practically you need to obtain information in online. Yes, but modeling give more direct, more common information. What is purpose of modeling in this case? Because you have model-oriented architecture. Why you need modeling and for these purposes? It is online information. It's nice you obtain this information and give this information to controllers. Why you need models?
So
What purposes?
as we made the models for not this only use cases, so it might be the next project which is similar to this but not the same, and we can reuse our models and make other platforms for these.
But you speak about the road traffic management system or about simulator of road traffic management system?
Road traffic management system.
Online road traffic management
Yes.
system. Okay, and at the certain slide. think maybe previously. Yes. What is the type of request?
So we have a web service like REST or so,
Yeah.
and we get a request of someone or some smartphone app wants to get special data. So we receive a request, and then.
But you produce it on the base of real data, not on the base of modeling. These services.
Sorry, I try to do it. I try to get it in German briefly, and then die Sachen sind auf realen Daten basierend und nicht. Die Frage ist dann, wenn das reale Daten sind und keine Simulation, warum so aufwendige Modellierung, glaube ich. Okay, so I think this might be a good idea to discuss this during lunch, because then you have lots of time and can draw together something for explanation.
Thank you.
Good. Then, thank you very much, Mirko. So, your certificate for the participation.
Thank you.
So, we are now coming to the third talk, RATNYČŽ. And he will talk about ultra-narrow band radio technology in high-density built-up areas. So we are curious to see what is hiding under this title. The floor is yours.
Thank you very much. So what is hidden behind this topic? Welcome everybody, my name is RATNYČŽ. I'm here to present the paper we did with Tomáš Heger. We are both from Czech Technical University in Prague. In the article or by him as a to promote the RFID technique in those times. But as we are approaching the next level of the technology, the miniaturization, and according to Moore's law, we have a great processing power with smaller devices. We have also technology life cycle, for example, for 2G, 3G, and I think that most or really important is also this big data analytics that is currently available or already available even as an open source. I think we are able to support some of the applications as I mentioned here, as is like for industrial sensors, home appliances, healthcare, transport, wearables, smart cities, etc. But really, this would be not possible to really evaluate if we would not have this big data analytics
like Hadoop, and for example we use the Hue on top of the Hadoop cluster for evaluation of the data, because of course one thing is that we can sense or we can collect the data, but the second thing is to make any evaluation based on these data. What does it mean, low power wide area technologies? As you can see on the picture, current technologies are not really supporting the use cases we need for this Internet of Things, mainly because they are focused on higher speeds or higher bit rates, data rates, and by that we are supporting only small areas, and also the consumption of battery is, thanks to the modulations and advanced techniques there, pretty high. In IoT we are speaking about consumptions that are tens of milliamperes. We are speaking about a long battery life, 15 to 20 years, low cost per device, and extended range support. So these are some examples. Out of that, we have selected a few parts that we focused on. We didn't focus on Sigfox or on security stuff, but we really focused on the evaluation of the technology that is called Sigfox. It is one of the examples that is currently, I think, maybe most widely installed or used for the Internet of Things. In some of the articles I found even that it is taken as some really like a basic or really most advanced Internet of Things example. So how it works? Sigfox was established as a startup in 2009 in France, and they are using one-hop start topology in ISM band, Industrial Scientific Medicine band. So it's in unlicensed spectrum. It's using rather small payload, 12 bytes for downlink and 8 bytes for uplink. You can see pretty amazing numbers, noise contribution, link budget. What is interesting and why I think it will gain some momentum currently is its business model, because they are actually installing the technology by using Sigfox national operators. So that means that for every country they will choose one operator that will install and cover and do the coverage or install the coverage for the whole country. And for example, in Czech Republic, where we did the measurements, it's a company called SimpleCell, and they made some agreement with T-Mobile or Deutsche Telekom company, and putting their receivers on the base stations of this operator. Yeah, so there are some more data that are supported for uplink. It's differential binary phase shift keying with 100 bits per second. Yeah, it's using in current version, that is version 2, 1920 slots, and that means that each slot is only 100 Hertz wide. Thanks to the regulation in the spectrum, we can use only 140 messages per day, not to break any law recommendation, because the transmission of the message is quite long. It takes up to roughly 2 seconds. Output power is at maximum 25 milliwatts, and we have 4 classes. This is the most powerful one, and we are using a random frequency division multiple access schema. So what we did for the evaluation, we had the opportunity to actually evaluate the Sigfox technology before the real rollout in Czech Republic to help with the evaluation to T-Mobile and Simple Cell companies. The setup was, as you can see on the picture, the Sigfox gateway is placed on some of the BTS or on the station. It can be 2G, 3G, or 4G radio station. Before we were transmitting via Sigfox terminal, we were using the portable spectrum analyzer Spectran HF6060 that was analyzing if the frequency is occupied or not. We were using the device in the 0U device class, that means with the maximum 25 milliwatts. We were using the module Telecom Design 1208 without GPS, and that's why we used a Raspberry Pi and connected with the GPS module, so we were able to actually evaluate the exact position of the measurement. The data itself are available to the customer or will be available via for example, like or the data are processed, they are taken to the backend, Sigfox backend, and then they are available to the user, for example, via REST API or HTTP callback. So the gateways you can see here. For the stationary measurements, it was only 4 gateways. 3 gateways were placed in Prague. Prague is a Czech capital. It has approximately 1.2 million inhabitants, and 1 was in the rural area, neighboring region. So what we were calculating was expected path loss model. That is valid only for the distances higher than Fraunhofer distance, and as a reference we were using free space loss model, and the result you can see here. But behind this data you cannot maybe really have the feeling. Here is as a function of the logarithmic distance, the path loss. You can see the variables of the model, but maybe really what we can see on the map, because this point is the highest peak of Czech Republic, and with this point we were able to have clear view or line of sight to all gateways, because Prague was, I don't know, more than 1,200 meters below this peak. So interesting is that based on this calculation, it seems that the 350 gateways shall be enough for coverage of the whole Czech Republic, compared to roughly 8,500 that are used for the mobile coverage in Czech Republic. So it's less than I don't know, 5%. So on top, or the second part of the article, you can read that we did also nomadic measurements. During those time, we already had 25 gateways installed in Prague and 13 gateways installed near the city. Here you can see where we were actually driving with our car, where we did the measurements. And that is our measurement car. We were focusing actually on the Doppler effect because our expectation was that because we have actually quite slow transmission that can take up to really these 2 seconds, the Doppler effect or shift can be can have really big effect on the data. Here are the reference values. As you can see, for the this is actually the angle or the velocity vector, and you can see that for the 0 degrees it's pretty high already, and that's why we focused on the evaluation of this Doppler effect. Message was composed to have the position, velocity, and unique identification to simulate future use of some tracking device, for example, that we can expect that it will have the same parameters. Here you can see some of the examples of the results. You can see that unfortunately it was really hard to do any big evaluation based on this nomadic results. We sum up the velocity to have some ranges, because in car it's really hard to have always on the road the same speed. So we have these ranges. You can see that the dispersion in lower velocities is a bit higher, seems to be, than in the higher speeds. Our conclusion is, and it's also our future work that I will speak about, that it is actually caused not by the speed itself, but by the change of the speed. Yeah, so this change of the speed or this acceleration is really causing the troubles to the technology. Here you can see that the number of the duplicates seem to actually show the trend that with the higher frequencies we have more duplicates, and it can be caused by 2 main factors. The one factor is that higher speeds we were actually able to have on the roads that were not directly in the in the city center. It was on some roads that are a bit bigger, and that's why there was no change in the speed in between the sending the message. So this acceleration was not such a important effect or on the measurement. And the second thing is that it was not in this most city center, so that's why the area was more rural, and we can expect better signal strength there in this not such a build-up area, and also this trend is not visible on RSSI or SNR evaluation, as you can see here. That is pretty stable among the speed. Yeah. So about our future work, we would like to focus on comparison with other technologies like LoRa, that is referenced as a more or less really similar technology. We are now cooperating on the evaluation of 3GPP technologies that are or that can be one standardized solution that will be offered to the users, and we have also from ETSI 1 M2M, etc. And for the nomadic measurements, we would like to focus on this effect of acceleration and its effect on the loss rate limits. On the other hand, we found out that the loss rate in our the mean loss rate in our measurements was roughly 20%. So it's not anything really limiting the use of the technology. Yeah, so that's it.
Okay, thank you very much for your talk. As you can see, we are offering quite a wide variety of topics today. So, any questions concerning the communication issue?
Yes. What frequency use this technology?
It's used. Actually, it uses in Europe 868, and in America 902.
And what type of modulation?
You can see that. We are using random frequency division multiple access.
Yes.
That means that actually every message is transmitted 3 times, and every time some random channel is chosen, or pseudo-random channel is chosen to be emitted, or where the message is emitted. By this, they say, or our observation was also that it's not so it's prone to temperature differences when you have a different with the temperature you can have a different frequency. So then the receiving antenna is actually receiving on all frequencies at once, like MIMO. So that's why they are actually prone, or this chipsets can be a bit more cheaper because they don't need to be temperature stabilized or compensated, as we also evaluated during our measurement this temperature differences.
Last questions. On the last slide with the diagrams. Is it? Yes, this one. What means red lines?
It's actually the average here.
Not at all. Average,
No.
I see.
Yeah, it was. Now you got me.
Sorry.
Yeah, this is the dispersion. I think we were evaluating what, I don't know, really, I'm sorry.
No problem.
Okay, so perhaps a remark from me. I think it's really good to see this kind of alternative communication technologies coming up, because I know from some projects with Australia, for example, lots of Internet of Things applications are getting more interesting if things are far away, because it's difficult to reach the machines and so on, and to send people there. In a city, it's usually easy. Besides the traffic jam, you can just send someone to check. But somewhere in the outback in Australia, it's getting more and more difficult to quickly send someone over to check, and then communication is playing a big role, because there is usually no. Well, in city areas, we are used to, of course, we have 3G or whatever LTE mobile connectivity, no big deal. But there are actually lots of areas in the world where IoT applications make a lot of sense that are not completely covered. So this is I think, a very good approach also to go into to enable those kinds of applications more. Thank you very much. And I have a certificate
great.
also for you. So
thank you
thanks
very
for
much.
participation.
Thank you.
So we can continue? Yes. Good. Okay, so our next speaker will be Fabian Wackermann, also from Dortmund, and he will talk about the change impact in product lines and about a study they've done there. So the floor is yours.
Thank you. As introduced, I'm Fabian Wackermann, and I'm one of the German guys from the University of Dortmund. And together with Christopher Brimp and Philipp Heisig, I did a systematic mapping study. So it's some kind of secondary study. And our topic was the change impact within product lines. So I divided the presentation into 3 parts. The first part is about the change impact in product line topics, just a brief introduction. And then some words about mapping study itself, because we are the only mapping study on this conference, so I will tell you something about it. And the last part is the conducted mapping study itself, so there are some results and I will present them. So let's start. There is some aspects in the automotive industry. There are many safety aspects at first, and on the other hand, there are always more demands from customers for more comfort in cars and so on, more entertainment systems, more functions within vehicles, and more connecting stuff. And there are these innovations nowadays are mostly driven by software. So there's a lot of increasing complexity, and to deal with it, there is some need for sophisticated variant management. So we can deal with these complexities within those cars. So there's also a complex supply chain within the automotive industry, and so it's good to have such a research area as the MLCA project, which we are doing in our research group. And MLCA address these issues by establishing a tool chain for embedded multi- and many-core software projects, and so you can simulate aspects as well, and exchange parts with your industrial partners, etc. And one of the outcoming of the MLCA project, and it's Sucedor, the MLCA for Public project, was the App for MC project. That's one official Eclipse project nowadays. So why do we need product lines and change impact? Yeah, because of the complexity. The automotive domain is among a broad variant, and we have got so many functions and so many specialized hardware platforms, so we just need product lines. And there's several classifications of product lines. The first classification we have is simple product lines, where it's defined as a simple set of products which are related somehow, and they share some common key features. And then we've got software product lines. That's the same thing, just within the software engineering domain. So there's another thing, the multi-product line, which is quite more complex. It's where we speak from a multi-product line when several product lines are combined. And then we speak about product families when we've got more disciplines within our product lines. So we've got hardware as well as software aspects, so it's quite more confusing and complex. So let's know why change impact is important, because when we've got a huge project, like in the automotive industry, it's quite common to have large projects. It's very likely that the system will change even within development time. And the implementation of these errors, the implementation of changes it's very likely to produce some errors, and some will be even complex to maintain, and especially in the safety domains, especially in domains like the automotive industry, it's very critical. And only by change impact analysis it's possible to identify and allocate those changes. So now some words about the mapping study. And as I introduced, it's some kind of secondary study, so there's nothing new as an approach or so. So it's just an analysis of research done so far by other researchers, so you have a broad overview. And so we classified and counted the publications which were done already, so there's an overview at all. And we identify and we tried to find research gaps, and the roots of the systematic mapping study itself is in the medical disciplines, because they really don't need only an approach and say, hey, it works. They are very interested in how well a medical product works for 10 people, 100 people, and their consequences. So Peterson adopted in 2008 the systematic mapping study approach into the software engineering domain, and they updated it later in the year 2015. So there are more and more systematic mapping studies, even in software engineering domains. So why do we do a systematic mapping study? We'll do it because of we can identify research gaps, and to have a systematic way of discovering unknown papers, unknown disciplines, and it's provide us a methodology which is quite scientifically, and not just saying, hey, we read a paper and so on. So now I'll give you a brief overview of our mapping results. We first defined our research questions. We conducted the search within several search engines, and classified our search results and mapped them within the categories we produced. And then we'll go on with some further analysis. So we have 3 research questions. So we wanted to know how many publications they are dealing with product lines, and also which are also dealing with change impact and product lines, because there's many publications about product lines and many publications about change impact, but not so many seems to be addressing both aspects. So that was one of our first question. And the second question was, is it a trending topic, or is it just done by some publications and not from interest anymore? And then the third question was about the sources for the papers and publications in general. So let's start with the conducted search. We searched within the well-known sources, ACM, Digital Library, the IEEE Explorer, Science Direct, DBLP as introduced on the keynote on the first day, and the base search engine. The base search engine is a German project which is a meta search engine for academic publications. So we think we have conducted the search within the most common search engines. So we excluded papers which were not peer-reviewed or not published, so you can't get them. And we excluded everything which was not in English, so it can be reproduced our study. And then we have some classification categories. The first classification category was the contribution classification, and we have towards papers which have just a brief discussion of an idea. We have got discussion papers which discuss a solution more in detail, and we've got an approach where several steps are defined for one solution, and then we have a tooling category where a tool is introduced to have a solution for a defined problem, and the last category was a case study, so there's an increasing solution. So the next classification we had in our mapping study was the product line classification, and there we classified the papers within 5 categories, 6 categories. So the category number 0 was those papers who addressed the change impact not in detail, or just naming change impact but doesn't do any further discussion of it. The first category, single product, there was then no product line concept given, but the change impact was addressed, and the other categories are increasing. Then a product line, that's a product line with no further context, so it's not said in the paper whether it's addressing only software or can be applied to hardware as well. The third priority classification was the software product line. That's the classification where software is explicitly addressed. And the fourth category, the multi-product line category, where several heterogeneous product lines are introduced. And the fifth and last category was the product families, where we have a combination of different system parts within a product context. So after all, that's our classification mapping result. So you've got on the left side the product line categories, and on the upper side the contribution categories. And the bubbles are indicating the number of publications. So as you can see, the most publications was within the software product line category. And because it might be confusing with those bubbles, we did the same in total numbers. So it might be easier to read or imagine how many publications were in those categories. There are only a few papers dealing with multi-product lines and product families, as you can see. Especially there is no case study within product families and multi-product lines. So another research question was, is it a trending topic? And to be honest, we can't say for sure, because there were publications increasing nearly from year to year, but it's not such a clear trend. So it's not so finite to say. But the product family and multi-product line papers were within the last years. So this might be an interesting research area. So we asked for the sources, and it's quite surprising that even the software product line conference had the most publications within the multi-product line papers, and the product family papers were totally mixed. But anyway, the software product line conference is one of the main sources. On this slide are only sources covered which had 3 or more publications published within. So, in a nutshell, so there are many, the CIA for software product lines has been addressed by some articles, or some more articles, and multi-product lines and product families together in a paper are very rare, and the change impact approaches seems to be a research gasp, and it seems to be that change impact analysis within a product line context seems to be a relevant and future topic for research, and because of the classification that there are now case studies for product multi-product lines and product families, it seems so that it will be likely that there are publications in the future. So the further analysis was that there are 7 articles within the product family and multi-product lines categories combined, and there were 3 which only matched the key words change impact, but they did not match the. They didn't discuss further analysis. They just said that there was an impact, change impact, and 2 articles directly addressed change impact analysis, but only one of them included hardware aspects. As you can see, the combination of product line and change impact seems to be very challenging. And one publication focused the evaluation of multi-product lines, and one article only describes the problem of CIA, but does not more discuss it in more detail. So, yeah. So that was the presentation as far, and there are 2 references for the mapping study, and yeah. So thank you, and any questions so far?
Thank you, Fabian, for your talk. Anyone, any questions? Well, then.
So maybe a little bit of context. How is software product line related to automotive industry?
The software product line?
Yes.
That's because the innovations in the automotive industry are nowadays driven by software. There are multi and many core systems within most vehicles. So there's software engineering in the car itself. So you.
Well, I expected a little bit another answer. The idea is that the way you assemble a car on a product line from different parts, different combinations of parts, the same way you assemble software from different components, different versions of components to get a variability, to get a different versions of a system which target different users.
Yeah, we've got this.
I'm right.
You are right, but the problem is that the real realization of a car consists of not only one product line; it's a combination of many product lines.
Multiple product lines.
Yeah, and that's a difficulty. And linking the requirements and constraints over many product lines with many partners and models involved is quite complex, and because of the life cycle of a car which is developed and then it's produced for more than some months, and so the supplier chain changes, and there might be other parts, and that's the main of the
That's why you need a software product line modeling tools.
Yes, and Amalthea does not only provides a tool chain for these issues.
Then you study software production line. You study the result function of hardware, because all producers today of cars has its own independent software.
They have different standards for exchanging information,
Yes.
and the MLCR project has one core system model which can be exchanged, and this should help the supply chain to simulate and put the constraints within the.
In this case, why you don't use, for example, ontology or taxonomy for description of the results of your work?
We did this because of the methodology of Peterson. He described in his first publication a keywording approach. So you read for example, the abstract, and then you'll extract some keywords out of it, and then you'll combine it with the next papers and map the keywords to the next one, and so on. It's described very briefly, and I think the updated version of him doesn't include the keywording approach anymore.
But do you study journals, for example, not only in software area? Because there are a lot of journals, for example, intelligent transport systems and so on.
We search through the search engines which I introduced, and the journals are included there. So they are included as well as other technical reports and such stuff. However, I think there was one or non-technical report at all.
Thanks.
Okay, thank you very much for this insight to a unusual approach to software engineering, while we normally just simply try out, see it works or not. This is an interesting insight into an approach to get more overview over a big growing research in the field. Thank you very much. So, and now we come to the last, final, but not least talk of the session. Now you will hear Fabian Knäher talking about self-configuring systems in Internet of Things, and about a study which is based on the model-driven prototyping approach. And Fabian is obviously from University of Applied Sciences in Dortmund as well. So thank you very much. Fabian, the floor is yours.
Yes, thank you for the introduction. My name is Fabian Knäher. I'm also from the University of Applied Science and Arts in Dortmund. And during our research with Eric, we developed this case study for self-configuring systems. Let's look on the agenda. First, I will start with a short motivation for our research and for the case study. Then I will show the domain of the case study, and after that, the specification of the case study, and I end with a short conclusion and maybe more current work and future work. So, our topic is the requirements engineering. I came from the requirements engineering. There we have an engineer who's tried to describe and develop a system based on the requirements he gathered from a stakeholder. So this is a very huge and wide area. So we focus on the development of self-configuring systems. Now this question, what is a self-configuring system? There we have a definition from IBM, and they say self-configuring means it adapts to a changing environment. This means there are predefined policies which the system uses to find the best configuration for the current situation. And such a same change in the environment could be leaving or entering component or deploying and removal of existing components. So now we know what is a self-configuring system, why are self-configuring systems important. And there we come to this keyword we hear all over the conference, the Internet of Things. There we have a definition from ITU, and they say Internet of Things is a network where physical and virtual things are communicate with each other, and these networks are very dynamic. We have entering informations or services from these things and also leaving. So the system that works in the Internet of Things has to configure and has to react on these changes and these new information or new services. For example, on the keynote of the last day, when we have this toothbrush and it works with a smartphone. What if we don't have a smartphone? What if it's broken or the battery is empty? Can we use the toothbrush? Or can we connect it to an iPad or other tablet or maybe a TV to brush our teeth? And so on. So, now the problem. When working in the area of self-configuring systems, we notice there are many approaches in the last years. And they all have a big problem with the validation. Because there's a lack on case studies for the validation and for self-configuring systems. Here are only some examples they use. It's a news website and the automated traffic routing problem. But for us, it's not really in the IoT where we have physical and virtual devices that communicate together and that we can build in our university. So our goal is build a case study based on IoT that have software and hardware components. And what we want with this case study, we want to understand, optimize, and compare different approaches on the development of self-configuring systems. So, our domain. We choose the domain of the smart city. I think everybody will agree that it's an example for the IoT. There we have the normal parts of the smart city: smart mobility, smart economy, smart living, or smart houses and smart buildings. And now there's the next problem: how to define a smart city. For us, we define a smart city as a city that uses information, communication, and resource-saving techniques. And with these techniques, it reduces the consumption of resources and raises the quality of the life. A very good example is Smart City Amsterdam. And they are really transparent in their projects, how they built it and what they are doing. And I think they are on a really good way to make City Amsterdam smart. Now we go a little bit deeper into the smart city, and there's the public lighting. This is an example from the industry. The company Electron AG has this product, Comlight ELI. They try to make the light smarter, and they equip it with radar sensors that detect moving objects. On the upper side of the figure, we see a small or a slow moving object. It only requires 3 lamps to make a safe way for the person. And on the other side, we have a car that's driving on a street, maybe a little bit faster, and there we need 7 lights. So the energy is safe because only the lamps that that detects objects are used to maximize illumination. The next example is IntelliStreet, and they make the light to a really important part of the infrastructure of a smart city. They add many new features to the lamp besides the lighting. This could be the smart street lights or digital street signs, where people can connect and can show which way they should take, or for video or audio announcements, and also for warning and many more things. And the last example is from Siemens. They invite a parking management system, not like the one we had before. They use distance and movement sensors to detect the parking slots right under the light, and then connects to other services or direct to cars, navigation systems, to show that there is a free space under this light. This would reduce the traffic inside the city, because there are no slow-moving cars around the blocks and looking for a free space. So now I came to our case study. What our focus was that we built a public lighting system that serves different functions based on the situation around the light. This means we monitor the environment and then react and change the configuration. This means we need sensors on the light to monitor the environment. These are like the examples from the industry: movement sensors, tri-light sensors, distance sensors, and hydro sensors. Then we need a connection to other devices and also to other lights. And as actuators, we use the color of the light, white, red, and blue, and the illumination, the intensity of the light. So our features. The main feature is light the street. There we have an arrow state, like it's called always on. This means if all sensors are broken and we can't secure that the way is safe for the people, we had to maximize the illumination the whole day. Then we have the time lighting. This is a mode that requires a timer, and depending on the queue time and predefined on and off times, they switch the light on and off. Then we have the light controlled lighting. This requires the tri-light or light sensor and reacts on the lighting situation. This could be maybe if we are on the day and it's very cloudy, it's kind of dark, so we put on the lamp. Both the time lighting and the light controlled lighting have a dynamic and a static mode. Static mode means when they're on, they have a maximized illumination, and dynamic means it also requires a movement sensor and detects moving objects, and then switch, like before we see on the figures before, from 20 to 100 illumination. The next feature is the parking spaces systems. This counts the parking slots and the cars and sends this information to the other systems. And we also added some kinds of feedback. We highlight free parking spots with a blue light when the car is searching in the area. Then our last feature is the ambulance warning. This means when an ambulance will pass the street and the street light, the color will change to red. So when we talk about reconfiguration, we need any kind of indicators when we need to reconfigure. So these are now the indicators. At first, for every sensor, we have an indicator if the sensor values if the sensor is broken or not. Then we have two that detect the movement Also if there any person or car is moving or object, and detecting twilight, the change in the lighting situation. Then for the parking assistant, we have the number of cars that are parking under the light, and the signal if a car connects to the system and asks for a free space. Then also for the ambulance, we also get a signal if an ambulance connects and says, I move to that street, and the people should be warned. Then we have 3 indicators for the time. Time is the current time of the system, of the light. Turn on time and turn off time depends on the, for example, the sunrise in this area. With all these indicators and all the features, we built a simulation. This is a software simulation, and we also built a hardware model of the street light. It's about 60 centimeters. I show a picture on the next slide. The simulation. On the right side, we have the control panels to change the environment and test with the indicator changes. This is example, the sensors are all working. Under the sensors, there we have 2 buttons to start cars. And under that, we have the control panel to add and remove parking cars. And with the Go button, we can simulate 24 hours of the street light and produce random events to see if the system works correct. In this example, we have an ambulance that passes right the street, and now we see that the light is red. So, to my conclusion, we invent a case study that is based on IT, that has software and hardware components, has a reasonable complexity for the validation, has software and hardware components, and is practical relevance as we based it on current products that are working or that are invented in the industry. Now I say future work. Currently we're working on a more fancy simulator we can put on as a web application with open access, so other researchers can use our case study and the simulation at their place. Also, we want to make our whole project with the framework and user guide, and also a guide to build the hardware, open source, maybe on GitHub, and supported with like an ICIST tracker and so on. Then the picture of our light. This is our first prototype. The head is built with many tape. We now a little bit further and have a 3D model for the head, and also printed it. I don't have a picture right now. And our goal is to have a small world of a street. This means we want up to 5 lamps. The prototype was about 100 euros with all the sensors, and we used the Raspberry Pi. And the second version with the 3D printed was a little bit cheaper. We are on about 80 euros. Our next steps, when we have the model, then actually, at the moment we have small boxes we put under the lamp, but in the relationship to IT, we want an RC car which connects to the street and simulates then an ambulance or normal cars that park under the street or cross the street. And then we're thinking about simulation more parts of the smart city. Maybe, for example, the police department. This could be when the police department makes statistics, how the criminals rise or the accidents rise. Maybe it's also an important information for the street light to change the configuration and see if it really works with the city. And I think that's also a very important part of the smart city, that they transfer the information to other parts of the smart city. So that was my presentation. Are there any questions?
Thank you very much, Fabian, for your presentation. Any questions? Well,
maybe a question from my side. We have expert on IoT. Did you notice also that there's a leak on proper case studies? Or do you have a good case study that we missed?
Maybe a brief comment from my side. I think that, for example, for the Sigfox technology, we were even struggling to find any article at all about the technology. So that was the first surprise. Secondly, when we spoke about the technology with some suppliers, I think that they are waiting. They are still waiting, and it seems to me that nobody wants to be the first one. And because the implementation, to me, seems to be rather simple in some cases. Yeah, it's not a rocket science to do some remote sensor, at least like with some simple use case, but still they are not actually at the market yet. So I totally agree that it seems that the most use cases, or the field is now at the universities to put relevant and interesting use cases for the market, because they are a bit afraid, I think, to invest some money. Even it can be connected with the technologies, because we have like 4 biggest technologies, and I think they are afraid to choose one and then invest on the one, and before the final one will be chosen, because I think there is no place for 4 or 5 technologies in the world.
What also is an important part is the security. I talked yesterday or 2 days ago with some person. We don't have any security in this case study in the moment, and that's also a problem. Nobody wants unsecured IoT. Everybody is afraid. Where goes my data and so on, and that's also a really hard part, and must be more work.
Especially with the case of open source.
Yeah.
So perhaps a comment from my side, besides the practical view why the industry isn't producing more case studies, why academia isn't producing more is, I think, because we are already having a hard time making a prototype. So something that is running if you do not look too closely at it. You know, something that is running somewhat, but you better not touch it when it runs. And for a case study, for real world tryouts, you simply need more reliable, more stable version of the thing, which means lots of bread and butter work, which is for academia somewhat difficult, because then you go to the next topic where you get quicker results for a paper, for whatever to publish. So I think, and for the industry, I agree, it's the problem of the first mover is seldom the one making the money and getting rich in the business. So they're all waiting, I think, for the first movers to burn their money and then to go in with the lessons learned as fast followers and then make business. So let's see what we manage together for that. Okay, thank you very much, Fabian.
It was a pleasure.
I would like to thank Christian for his excellent chairmanship. It was a pleasure for us.
It was a pleasure to come here, and I'm looking forward to come next year as well.
Sure, we are waiting for you.
Good, okay. Then I want to thank all the participants for being in the session, and we stopped roughly half an hour earlier than we needed, if I'm correct. Yes. So we are a bit more than half an hour ahead schedule. That means you can now ponder a bit about your trip home and then enjoy lunch and then the closing ceremony. So see you all at the closing ceremony. Thank you very much.